If you try to wash greasy, dirty hands with just water, you're going to hit a chemical wall. The water simply beads up and rolls right off the grime, leaving the dirt and the microbes entirely intact. This happens because water molecules are polar, acting like tiny magnets that only want to stick to other polar molecules. Oils and fats are nonpolar. To water, they are effectively invisible, making them impossible to wash away on their own. To bridge this gap, you need a chemical translator. You need sodium stearate, better known as soap. A soap molecule has a split personality. A polar hydrophilic head attracts water, while a long, zigzagging lipophilic tail seeks out oils. This structure simultaneously grabs both substances. The head locks on to passing water, while the tail embeds into the grease. By forcing these incompatible elements to connect, soap transforms a passive wash into an active, microscopic extraction mission. When a drop of liquid soap first hits a pool of water, it triggers an immediate and incredibly violent physical reaction. This is the Marangoni effect in action. The soap instantly lowers the water's surface tension at the point of impact. The surrounding water, which still has high surface tension, pulls away forcefully, dragging the surface layer outward in a microscopic tug-of-war. There is also a thermodynamic drive pushing the soap molecules further into the surrounding environment, creating a highly volatile situation at the molecular level. The long lipophilic tails experience what chemists call hydrophobic interactions. They are actively repelled by the water molecules. To escape, they frantically search the environment for anything nonpolar to hide inside. Soap actively manipulates fundamental fluid dynamics to hunt down and isolate nonpolar targets. Those targets usually include the lipid cell membranes of bacteria and viruses. These membranes are fatty, nonpolar barriers. Escaping tails forcefully wedge into the microbe's protective layer. Packing in, they create massive strain. Pulled by water, they act as crowbars, prying the pathogen apart. Reaching critical micelle concentration, they form spherical micelles, trapping the destroyed germ fragments securely inside. This process successfully converts immovable, insoluble biological threats into isolated, water-soluble prisons. To actually manufacture this precise molecular tool from scratch, we rely on a violent chemical process called saponification. It is a strange historical irony that our most effective cleaning agent is born by boiling raw animal fat together with caustic ash. This raw chemical mixture is incredibly efficient at tearing apart microbial membranes, but it does not discriminate. If left unrefined, it will strip the natural oils and moisture straight out of human skin. This chart analyzes moisture levels in human skin after the repeated use of a basic soap made from goat's milk and lye. It shows a clear trend. Across the test states, hand moisture levels steadily declined, proving raw saponification provides zero hydration. To prevent this, modern soap formulas include glycerin or specific oils to protect the skin while the molecules do their work. But the chemistry requires human assistance to finish the job. We must provide mechanical agitation, scrubbing our hands together, to physically force soap molecules down into the skin's microscopic crevices where dirt gets trapped. Finally, the hydrodynamic drag of running tap water grabs the outer shells of the micelles and flushes them down the drain. Hand washing is the deployment of billions of engineered molecular crowbars, a coordinated effort to manipulate physics, construct cellular prisons, and mechanically extract invisible threats from the body.